Hi, and welcome to today's video where we are going to be looking at something called mechanical advantage, a scientific concept. Before we can get into that though, it's probably a good idea to have an understanding about what mechanical advantage is. So the definition of mechanical advantage essentially is when machines do work for us. We put in some type of an effort and they output some type of an effort as well. And the mechanical advantage simply tells us how much they are putting out based on what we are putting in. So let's talk about that today and let's look at what we have here. We have a first-class lever. You might recognize this from a playground as a seesaw where if you and your buddy hopped on it, they would balance each other's weight out. One would push, so on and so forth. In this case, this is a technical term is called a first-class lever, and I'll explain why that is. On this side, we have a load, so there is something that is already weighing this down. That load is what we are going to be trying or attempting to pick up. In the middle here, we have what is called a fulcrum, and it separates the load from what happens over here, and what happens over here is the effort. So in order for us to lift this object up, we need to apply force or an effort to try and get it up. Now, what we are going to be talking about today with mechanical advantage is how much mechanical advantage does this give us, and is there anything that we can do to make it more advantageous for us, or anything that we can do that would allow for us to lift this object using less work or less force. And there is, so we'll talk about that. So first things first, we've already given this a value. It's 50 newtons to pick this up. So in order to determine mechanical advantage, there are two different ways that we can do this. The first one is we can actually measure the amount of force that it takes to lift this object up using something like a Newton scale. That's really tough to do on glass, and sometimes it's really tough to do in real life. So what we're going to do then is we're going to do option number 2, which is where we are going to measure what is called the effort arm, and we are going to divide it by the load arm. So let's pretend that this right here, this whole thing, this board, is 100 centimeters. And if you take a look at where our fulcrum is located, it's pretty much right in half. So if we are using the mechanical advantage of effort arm versus load arm, or divided by load arm, then essentially our mathematical formula for this is mechanical advantage is effort arm divided by load arm. And if this is 100, we know half of 100 is 50, so the mechanical advantage then becomes 50 divided by 50, which gives us a mechanical advantage of 1. Now that 1 is really important, because that 1 tells us that this machine is putting out 100% of what it is that we are putting in. Let me put that into terms that might be a little easier to understand. If I put 1 Newton in here, it's going to output 1 Newton, or 100%. If I put 5 in here, it's going to output 5. So it's doing exactly the same as what I put into it. Now, is there any way that we might be able to do this, any way that we can manipulate this first-class lever in order to make it easier? Well, there is, actually. We know we can't do anything with the overall length of the board because I can't extend the board. But what I can do is I can move the fulcrum. And if I move the fulcrum closer to the load, then technically I think I'm extending one of the arms. So let's try that. So I'll erase this fulcrum, and I'll do this in pink. Let's say that I'm going to go 3/4 of the length of the board. Okay, so that's about 3/4, we'd say. And what this means is that now, instead of where the effort arm was here and here, now the effort arm has actually extended a bit. So now the effort arm is traveling from the fulcrum this distance, which would be about 75%, or in this case, 75 centimeters if the board is 100, like I said right off the top. So that is going to change our mathematical formula a little bit. What that means is that we are going to have mechanical advantage equals still effort arm over load arm, and the mechanical advantage is now going to change the measurements a bit. We're going to have 75 versus 25, or divided by 25, which is going to give us a mechanical advantage of 3. So that means that the machine is now doing 3 times more of the work than when I had the fulcrum right in the middle. So again, in terms that you might be able to understand, or that might be a little easier to understand, is that if I put 1 in here, I'm taking the input force, or what I'm putting in, the effort, multiplying it by 3 to determine the output force. I put in 1, it puts out 3. I put in 10, it puts out 30. So wait a second. So if this was 1 to 1, I would need 50 newtons to lift. But in this case, if this is outputting 3 times as much effort, then technically if I took this, 50, and divided it by 3, I would end up with 16.67 or something like that, 16.7. If I take 16.67 and multiply it by 3, I get more than 50. That tells me for sure mathematically I have enough effort to lift this, whereas before I needed 50. So the machine has gotten more advantageous for me by simply moving the fulcrum over. Let's see if we can make it even more advantageous. Let's erase this fulcrum, and let's put a new fulcrum in. Let's do this in orange. And let's make it about 90% of what the board is. So we know originally this board was 100 centimeters. This is now about 90% of that, or 90 centimeters. So our mechanical advantage then becomes MA equals effort arm over load arm. Mechanical advantage is 90 divided by 10, 10 being what's left. This is the load arm. This is the effort arm. That gives me a mechanical advantage of 9. Wow, that's fairly significant more than what I just had. 3 times as more, in fact. So that means if I put in 1 on this side, because I've moved the fulcrum so much closer to the load, it's going to output 9. So if I put in 10, it's going to output 90, which means that I'm going to even require less effort than if the board was 3/4 of the way through. How much less effort? Well, if I was trying to determine what effort I needed, force in, that's going to be equivalent of 50 divided by my mechanical advantage. 50 divided by mechanical advantage would give me my force in, and that's going to be 5.555 or 5.6. So if I multiplied 5.6 newtons by 9, I get over 50. That's more than enough than what I need in order to make this work. So this is the concept of mechanical advantage, and the big idea about this is that if we are using a first-class lever, the closer we move the fulcrum to the load, the easier the work is going to be. And mathematically, we have shown that. Originally, we started out with a half and half. So it was 50-50. I put in 1, it puts out 1. Then we moved the fulcrum closer to the load, and we were able to find out that if we were 3/4 of the length of the bar, it would be a 75 to 25 split for a mechanical advantage of 3, which meant that I would need 1 to 3, 2 to 6. It would be multiplying my input by 3 times. And then I got even closer to the load, and I found myself getting a mechanical advantage of 9. So I extended the effort arm. It made it even easier for me to lift this 50 newtons. I put in 1, it puts out 9. I put out 2, it puts out 18, and so on and so forth, essentially following the same concept. Whatever I put in, it's going to multiply by the mechanical advantage on the other side of the load. So this is mechanical advantage. If you need to rewatch the video, please do so. If you have any questions or comments, please comment below. By all means, please share and subscribe this. And again, thank you very much for tuning in and watching.